Welcome to SCP-140, our final discussion, chapters 29 and 30 of your text. These are the chapters that deal with the subject of cosmology, which is the study of the universe on the largest scales. We're interested in where the universe came from, how different things are distributed throughout the universe, and ultimate questions about what will happen in the future, even beyond when we are no longer here on the Earth, when the sun has completely exhausted all of its nuclear fuel and turned into a white dwarf, when our galaxy has now disappeared from view as all the stars have lost all of their ability to shine. What will happen at the very end? This is what we'll try to answer. Well, we don't really know the answers, but we'll give you some speculations. When we talk about cosmology, the universe on the largest scale, it's a very difficult subject because we often want to take a view of the entire universe, and we sometimes do that by making a terrible, terrible choice of stepping outside of our view and looking at it as though we can separate ourselves from the universe. That's not how things go. We're always going to be confined to this place, this reality, this extension all the way across to as far away as you can imagine, looking out into space and back in time as far back as possible. That's what we mean when we talk about the universe. Nevertheless, you'll see diagrams like this, which try to show how time and space might be related. Going back in time 13.8 billion years is how long it takes to rewind the clock backwards so that all the galaxies are on top of all the other galaxies. Remember, Edwin Hubble discovered that the galaxies were all moving away from each other, not just from me, not just from people here on Earth and in our Milky Way galaxy, but in every galaxy. No matter where you were in the universe, as you look out, you see the galaxies receding away from you. This means the universe was expanding. But if you look back in time, it means the universe was contracting. And in fact, as we look out into space, we're looking back in time. So the further away we look, the smaller or more compact is the way to think of it, the universe was, more and more dense. And as you go back to the furthest moments, eventually everything is so dense, it's right on top of everything else. We call that first moment, when everything was at the highest possible density, the Big Bang. And at that point, things began to expand. We can see lots and lots of objects that go very, very far away, that are getting closer and closer to that initial high density, high temperature event in the beginning of our universe. But we can never see all the way back. We're blocked by some interesting features of our own universe. But the farthest back that we can see is something along the lines of 12 to 13 billion light years away in terms of just looking at the distance multiplied by the speed of light. And that's what we can see in this diagram here. But also in this diagram, you get a little cartoonish look as to how the universe's expansion has changed over time. Right now, the universe is expanding at a certain rate. In fact, we call that rate 70 kilometers per second per million parsecs. A parsec is about 3 light years. So this is about 20 kilometers per second per million light years. It's a pretty fast speed as we go out there. But in the past, the speed was different. In fact, in the past, the speed was a little bit slower. And that expanding universe, expanding more slowly than today, means that the universe is speeding up in its expansion. It's accelerating in its expansion. And we've measured that acceleration by carefully mapping the rate at which things are moving apart from each other at different epochs in our universe. And that tells us that there's an extra push out there in space, something called dark energy, which is causing the accelerated expansion of the universe. This was observed by looking at the careful rates at which things were moving apart, and was also seen in other evidence when we looked at how much energy was in the whole universe. And from first principles calculated that there was about 70% of the energy unaccounted for. And if you put that 70% in a form of energy that's very strange, that just happens to be energy that just permeates all of space, it causes exactly the rate of expansion accelerating that we see in our universe. This is the evidence for dark energy, a very, very mysterious form of energy that exists apparently as a phenomenon that we really haven't explained well. Our best ways of trying to get our heads around this give us wildly incorrect results. The best we can say is that dark energy is something of a mystery. There are calculations that point to it that explain that this is probably what's going on, but they are inconsistent enough that it's hard for me to say that we know for certain what's going on. So we stick with the dark energy, we allow it to exist. We say that this seems to be the thing that is dominating our universe's energy budget, but we don't really have much more to say about it. We don't really know what it is. If you go back further in time, the universe actually was expanding faster in the past than it was at those times that were sort of intermediate between now and then. And this was due to the fact that the universe was full of material, matter, that was kind of pulling it back in on itself in a slowing expansion. This is when gravity slows down expansion. And then the furthest back you can go, you end up in the Big Bang. The Big Bang is the earliest moments in our universe, which are actually well calculated and accounted for. We know a lot about nuclear physics, high density and high temperature environments from experiments here on Earth, but also the calculations that we do to explain those experiments. And that gives us a pretty good understanding of the conditions in the earliest parts of the universe. Steven Weinberg, a famous physicist who studied these subjects, wrote a pretty famous book called The First 3 Minutes, which explained what happened in these early moments of time to create the earliest and the first things in our universe, which were the simplest nuclei and atoms that then distributed out and eventually, after enough period of time, formed all of the material and structure we see in the universe around us today. But there's also a huge component of our universe that is gravitationally bound, that's mysterious, and that's the dark matter. We spent quite a bit of time last lecture discussing the evidence for dark matter, but we also see it in the expansion of the universe. The way that the expansion slowed down early on, the amount of material that we seem to see, according to various measurements that we make, indicate that something along the lines of 90% of the matter in our universe is this form of dark matter, invisible, not interacting with us, basically stuff that we can't see except through its gravitational interactions. Also a mystery, perhaps a little bit less of a mystery than the dark energy, but a mystery all the same. That means something along the lines of 95% of the universe's energy budget is extremely mysterious. It's stuff that is so non-interactive with us that it permeates and is 70% of everything that's around us, but we do not notice it on a day-to-day basis. This is a little concerning. This mystery, on the one hand, is something that we don't really understand, but it's also exciting. It means that there's a lot left to learn, a lot left to explore. And I'm sure in hundreds of years, if this class is taught, there will be some amazing new understandings and insights into what this stuff really means. But for right now, it remains a mystery. The dark sector of our universe dominates everything, but still not something we understand. But we do understand that the universe is expanding, and we can explain a lot of phenomena according to that expansion. One thing that we can explain is the redshift of galaxies. We said that galaxies are moving far apart from each other, but another thing to think about is the light is moving between the galaxies. The things that we see according to these distant galaxies is the light traveling from that galaxy over millions or billions of years and then eventually reaching us. In that time, the universe expands, and that expansion actually has the effect of making the wavelength of light longer than it was when it started. That's what we call a redshift. So there's one way of thinking of the universe as everything moving away from everything else, the classic Doppler universe effect. But the other way to think about it is that the expanding universe imparts that redshift naturally onto light as it's traveling through the universe. This is something that is predicted directly by Albert Einstein's theory of general relativity and is a pretty amazing result. Had Einstein realized that his equations predicted this, he could have anticipated that the universe was expanding when he first wrote down his equations in the 1920s. Unfortunately, he wasn't able to do that. He didn't quite have the ability to make that leap. And so it was left to others to come up with that explanation and understanding. As I mentioned, depending on what's in the universe, you can have different rates and different histories of acceleration. A universe that has a lot of material in it will tend to slow down in its expansion. And sometimes, if there's enough material in our theoretical universe, it will end up collapsing back in on itself in something we call a big crunch. That's a model that we see over on the left. And for a long time, we didn't know how much stuff was in the universe. So we presumed that this was a possibility. We could be living in a universe that started with a big bang and ended with a big crunch. And some people presumed that that meant you could, after the big crunch, have another big bang. And you'd have this oscillating cyclical universe repeating over and over again. Later, people realized that there's probably not enough matter for that to happen in our universe. And so they came up with a different sort of universe that expanded, but it only expanded just. It never collapsed back in on itself, but everything eventually got to a maximum distance apart and never got further apart. That was one theory of the universe. Another theory was that if you had no gravitational interactions whatsoever, you could have a coasting universe where everything expanded at the same rate at all times, moving farther and farther apart from each other. But that's not the universe we live in. We live in an accelerating universe that's seen all the way over on the right. Well, really, it's a combination. Earlier on in the universe, it was a decelerating universe. Now it is an accelerating universe. One thing that you can see is as the universe is theorized, there is a different point in the past that corresponds to the Big Bang, depending on what kind of expansion rate you're experiencing. You can work out why that would have to be, but it's visually seen in this diagram here. This is another way of talking about that. Here are the different universes that we were talking about. Our own universe is number 4, but we also talked about universes that were decelerating, numbers 1, 2, and 3. And each of these universe theory models that we show have different rates of expansion where they are getting bigger and then, in the case of 1, get smaller, back down to a big crunch. And some of them get bigger and grow infinitely forever, and some of them accelerate away, like in 4. And you can see that that gives you different histories for our universe as well, different times for when the Big Bang occurred. So the fact that we live in universe 4 tells us precisely when the Big Bang had to occur. So what happened in this Big Bang moment? Today, we are about 10 to the 17 seconds after this initial event. But you can run the clock backwards, and if you use logarithmic counting, you can keep getting to shorter and shorter intervals of time when the universe was denser and denser and denser, never quite reaching infinity, but reaching extreme conditions. So for example, if we go back to about 10 to the 10 seconds after the Big Bang, we have the moment when atoms formed. If we go back even further to about 10 seconds after the Big Bang, electrons and positrons first formed. 1,000th of a second after the Big Bang is when the protons and antiprotons formed. If you go back earlier in time than that, their energy level was so high that things were basically able to change in and out of light and matter. There was no difference between the two of them. We call that asymmetry. How that happens is that when you have an extremely high amount of energy, you can spontaneously form matter out of light. There's enough energy in the light to form electrons and positrons. Then they annihilate together and form more energetic light. And that goes back and forth, a kind of an endless cycle. We call that radiation domination in the early universe. If you go back further than that, there was a time when all of the forces we see around us, the gravitational, electromagnetic, strong nuclear force and weak nuclear force, were unified into one. The universe becomes simpler in a way as you get to higher temperatures and higher densities. Things that look different today were the same in the past, but you didn't have things like atoms. You didn't have things that distinguish between matter and light. Everything was sort of the same. And that's, in that sense, we talk about the universe being very symmetric. The earliest era of the universe goes back to about 10 to the minus 43 seconds after the Big Bang, if you can imagine that happening. This is really where the understanding of our knowledge of physics ends. That amount of time is so short that when you calculate what would happen on those scales, you end up with a confusing clash of two theories, the theory of general relativity and the theory of quantum mechanics. To understand what happens at those levels, you need a new theory, something called the theory of quantum gravity. This is a theory we don't yet have. There are candidate theories for quantum gravity. String theory is perhaps the most famous one, but we don't have strong evidence for which one is correct. And trying to do calculations with them sometimes gives wildly different results from each other. So we don't really know what's going on at that time. But it's one of the areas of further research. It's something that we hope to really understand. And you can see at those extremely early times, extremely high temperatures, the universe was very different than it is today. Here's an example of different things that happened in the universe at different moments in time. 300,000 to 700,000 years after the Big Bang is the moment when atoms were first formed. Before then, electrons and protons were separate from each other. And there was so much energy in the universe that if they did try to combine, immediately they would get hit by high energy photons and end up splitting, ionizing. In the first 3 minutes, the energy level was high enough that in fact nuclei weren't able to form until after 3 minutes things cooled down enough so that you formed the simplest nuclei, and you can see them here. There's protons, which are hydrogen nuclei. There's deuterium, which is a proton and a neutron combined together. There's something called helium-4, which is the simplest and most abundant form of helium. And then there's helium-3, which is a different form of helium which exists in our universe, but is a lot more rare. If you go back to 1/100th of a second after the Big Bang, even those individual protons and neutrons didn't exist. And instead, you were dominated by a sea of electrons and positrons forming spontaneously out of light, gamma ray. It was such high energy and such high temperature that there was no difference between an electron and a photon, a ray of light and matter. So this is the way to think about the universe. As we look out, we're looking back in time. And there's a moment at which we can't see any further back. This is the moment at which the atoms were formed, and all of that light that was bathing the universe and keeping it at high temperature in that radiation-dominated phase ended up streaming out in all directions, and we can still see that light today. We call that light the CMB, the cosmic microwave background. It's the high energy material that ended up forming photons, rays of light, after about 300 to 700,000 years, and left behind the atoms of the early universe that would then go on to form all of the material you see around you today. The CMB has been redshifting for billions of years. It started off as very high energy photons and has now transitioned into the radio part of the spectrum, in particular the microwave part of the spectrum, at about 1 centimeter or so of wavelength. The analogy is when you look up at the sky on a cloudy day, you can see very clearly up to that first layer of clouds, but you can't see beyond that first layer of clouds. The light from the sun is coming through the clouds and is scattered all around, and then streams freely at the bottom of the clouds, in the same way that the light from the Big Bang is scattered all around in the early universe. And then at the point where atoms are created, then freely streams off until it reaches your eyes today. If you measure that light from the early universe, the CMB, you find it matches a very beautiful sweeping curve. This is a black body spectrum, the same black body spectrum we were looking at with stars, but at a much more accurate and precise level. The black body spectrum from the CMB is the most accurate black body spectrum ever observed in nature. It absolutely amazed people when it was discovered in the 1990s to be as close to a black body as it was. This is actually very strong evidence for the Big Bang, for the fact that there was this moment in time when the universe was very much the same everywhere, where all of the material was basically even throughout. You can't get such an even spectrum in any other way. The only way you get it is by having these models, which allow for a universe to be basically homogeneous and the same all the way throughout this early moment in time. Today, the cosmic microwave background measures a pretty cool 2.73 Kelvin. And because we see it in all directions, we can say with some amount of truth that that's essentially the temperature of our universe. Here are some of the observations that have been made of the cosmic microwave background, including the latest one, which was made by the Planck satellite, that gave us the best picture ever taken of the cosmic microwave background. The red spots are a little bit hotter than the cold spots, but the difference in temperature is something like 1 part in 100,000. It's a very, very tiny difference in temperature. Measurements that are really difficult to make with regular thermometers. You need special space instruments to really do these measurements. And here were the 3 most famous ones. The first one was called the COBE, which was the Cosmic Background Explorer. The next one was called WMAP, or the Wilkinson Microwave Anisotropy Probe. And the last one was Planck, named after Maxwell Planck, who was the first person to really describe that black body curve we've seen. The hot spots and cold spots correspond to slight overdensities and underdensities in the early universe. Those overdensities end up forming the seeds for the galaxy clusters and superclusters we see in our universe today, whereas the cold spots end up forming the seeds of the voids that we see today. Another thing that we can test by looking at the cosmic microwave background is the geometry of our universe. We don't often think of this, but there's not a particular reason that the geometry we use in our day-to-day lives, which is this Euclidean geometry on a flat sheet of paper, has to be the geometry we see throughout the universe. Here on Earth, in fact, if you were to try to measure a triangle that was large enough, you would find that the angles in the triangle didn't add up to 180 degrees. I can start at the North Pole, go down all the way to the equator, turn a right angle, go a quarter of the way around the Earth, turn another right angle, and go back up to the North Pole, and I'll be at 90 degrees to where I started. 90 plus 90 plus 90 is not 180. No, in fact, it is 270 degrees. But I have 3 straight legs of the triangle, and they add up with the angles to 270 degrees. This is because we live on a sphere on our planet Earth. Our universe could have had a similar sort of geometry. We call that spherical space or closed geometry. Or it could have a geometry where triangles were bowed in, where the angles in the triangles added up to less than 180 degrees. We call that hyperbolic space. But that's not where we live. We actually do live in a universe where the angles of a triangle add up to 180 degrees if you were to reach them all the way across the universe. And we can tell this by looking at the shapes in the microwave background and the sizes of these hot and cold spots, understanding what the evolution would imply and how things would have to change over time. That tells us that the universe is flat. And that flatness is a measurement of geometry. And it's also telling us something about how much material has to be in the universe. Because that material in the universe also not only changes the way that the universe behaves in time, but it also warps the space. It curves the space of the universe. And if it's exactly balanced, we end up with a flat universe, which is what we live in today. This is how we actually figured it out. You look at the distribution of hot and cold spots and you model what it would look like under different conditions of different geometries. And you find that the best match is when we say we have a flat geometry, a flat universe. But a flat geometry in a flat universe requires a certain amount of energy. And that amount of energy in the universe has to be made up of the energy associated with matter, E equals mc squared, the energy associated with dark matter, and the energy associated with dark energy. The amounts that you add those things up to are also going to dictate how hot and cold various spots are and how big those spots are in the cosmic microwave background. And when you do all of those calculations, you find that you match very well the argument that I was saying in the beginning, that the universe is about 95% in the dark sector. About 5% is the normal matter that you and I are made out of. We call that baryonic matter. Some 25% or so is the dark matter, and the remainder is the dark energy in our universe. And this seems to be where we live. This seems to be the situation that we find ourselves in. So this is a way of thinking about that. Ordinary matter, 5%, dark matter, 27%, and dark energy, 68%. But it's a little bit worse than that, because the ordinary matter is not always or even close to being in the form of what we would need to be human beings, for example. Most of it is in the form of hydrogen and helium. Less than 1% of it is in the form of stars. And less than 1% of that is surrounding the stars and planets, which is the material that we're made of. Over time, this discovery has really kind of confused people. In the 1970s, if we were talking about what the universe was made out of, we did know about dark matter, but we didn't know about dark energy. And so we thought that dark matter was probably just stuff we hadn't yet found. We called it ordinary dark matter. And then there was ordinary visible matter. It wasn't until the 80s when we realized that, yeah, this dark matter can't be the same as the stuff that we're made out of. It doesn't interact in the same ways. It's not just hiding. See, if it was regular matter, we'd still be able to see some of its signatures. We'd be able to see it every once in a while when it blocked out light, or if it glowed at very low temperatures, but we didn't see that. And so we know that it's not interacting with electromagnetic waves in the same way that ordinary matter does. So it's this exotic dark matter. But in the 90s, we discovered that dark energy seemed to be dominating the universe, and we ended up with the pie slice we see now. We haven't had much of a change since the 1990s in our understanding of what makes up the universe, but the mysteries still remain. We still haven't detected dark matter, and we are no closer in really figuring out what dark energy is. This is a normal diagram that people give to try to describe all the things that are happening in the universe as a whole. There's some Big Bang expansion that happens over 13.77 billion years. The first stars don't show up until about 400 million years, and there's a period of time between when the cosmic microwave background was produced, about 375,000 years after the Big Bang, and when the first stars show up 400 million years later, that are called the dark ages. This period of time is not just dark in the sense that there aren't any stars, but it's also dark in the sense that even if there was light that's being produced, it ends up getting absorbed very easily by a lot of the intervening material. If you could go back before the cosmic microwave background, you can calculate some things that happened in the early universe. And you find that that evenness of the cosmic microwave background leads us to understand that there was a moment of time when things expanded really, really rapidly. We call that inflation. Out of perhaps some quantum fluctuations that we don't quite understand. The early universe may have been very, very different than the universe we see today. But these quantum fluctuations at the early universe, although they could have been very bizarre, end up becoming very smooth under an extremely rapid expansion. And this rapid expansion was first worked out in the 1980s as people began to calculate what possibly could have happened in the earliest moments of the universe. This inflationary universe that we talk about today seems to be the best explanation for the smoothness, the regularness, and all of the matching information that we're getting from the cosmic microwave background in the distribution of material throughout the universe. So this is the inflationary model. In the early universe, something weird was happening that we really don't have access to. But whatever was going on a very simple interaction occurred, which caused the universe to expand very, very rapidly, very exponentially. And at that point, we end up with a very smooth and even and flat universe. It explains the geometry. It explains why the cosmic microwave background is such a perfect black body spectrum. And it also explains the rest of the balance that we see in our universe. So this is the evidence for inflation, kind of coming off of a model. If we were to just extrapolate back from the expansion that we see, we might not expect everything to be as smooth and even as we see in the cosmic microwave background. Another way of thinking of inflation is to imagine an ant on a balloon. The ant might see some strange curvature on the balloon, but if you blew the balloon up really, really rapidly, eventually that balloon would look very close to flat. And that ant would think it's living in a flat universe. So we might live in a bigger universe than we can see, than we can be accessing, that might not be so flat. But because of inflation, it basically ends up that way. At the time of inflation, things then start to expand and cool off. And we end up forming all of the things we see in our universe. The idea is that as you go back in time, energy densities increase and things start to unify. They start to look the same. The earliest moment, all of the forces may have been unified together in one theory of everything, one super force. And then at the earliest moments, right about perhaps before inflation happened, gravity ends up being a separate force from the rest of the standard model forces, the strong, weak, and electromagnetic forces. Then at about a temperature of 10 to the 27 Kelvin, that's a pretty high temperature, the strong nuclear force splits off from the electromagnetic and weak force, which at that time we would call the electroweak force. That's at about 10 to the minus 35 seconds after the Big Bang. That's usually the time that inflation is described as happening. At about 10 to the minus 12 seconds after the Big Bang, electromagnetism and the weak force, which is the force that describes radioactivity, split apart from each other. And at that moment, we start to explain the existence of subatomic particles, electrons, protons, and quarks, all of which will eventually form the normal matter we see around us today. So that is our exploration of cosmology. There's a lot more to be shared about this subject. The calculations are pretty incredible. They're things that I think are really exciting to do, but they require quite a lot of mathematical insight and some understanding of the physics of extremes, general relativity, quantum mechanics, nuclear physics, and the like. If you get interested in this subject, you have to spend many years learning all of these things to really put all the pieces together. But it's sort of amazing once you do that they all fit in the way that they do. This is the description we have of our universe. And there are all these mysteries left to be explained. Did inflation really happen? Or is there some other explanation that can allow us to have the smoothness of the cosmic microwave background and the giganticness of our universe? Is dark energy and dark matter the simplest model that we can come up with, or is there something else going on? Is there some new way of thinking about these things that we're missing? It's unclear. These mysteries remain to be solved. Perhaps there's new observations that are needed, or perhaps all the observations we need are just there. It just requires somebody to put them in the right order. It's not clear. Over the course of my life, I've seen this whole understanding of the universe develop. As I was a student and went into graduate school, all of these measurements came out to really solidify this story that I'm telling for you. But since then, not much has happened to move us beyond that explanation. The mysteries remain, the questions are still questions, and we don't have resolutions to them. I'm hopeful that in my lifetime breakthroughs will happen, but I can't predict where they will. No one would have predicted the existence of dark energy in the early 1990s. Dark matter wasn't a thing that people even thought could exist before the 1970s. We had a very different conception of the way the universe behaved before general relativity. No one thought that the universe was expanding. All of these discoveries have led us to new insights into what the universe looks like as a whole. And there certainly will be new ones as we move forward. So I hope you enjoyed this exploration of all that is. And maybe this will give you some inspiration to look into some of these matters yourself, learn a bit more. And who knows, maybe you'll be the one that discovers what the source and true understanding and underlying explanation is for all of these amazing things that we see around us.